Okay, did you guys get the alert? Nice. Cool. So I'm just gonna take a moment here to just give an intro for the Y Talks. So Women in AI organizes these Y Talks, and specifically I organize them. I look for speakers. So if anybody that's watching these knows someone that works in AI that would be a good speaker, has a really good topic, please let me know. Get in touch. And otherwise, we do try to kind of diversify like the topics that we cover. AI is a wide field. It can mean a lot of things to a lot of different people. And the aim of these talks is really to, twofold: to educate and also to give people ideas about what kinds of careers they can go into, or if they're working in any one specific field, what that means, what sort of avenues they can pursue. So with that said, I'm gonna introduce MaryLena Bleile.
Bleile.
Bleile, all right. And what I really liked about MaryLena is, actually, I'll just speak directly to you. What I really liked about your background, MaryLena, was that you have this like mathematics background, and you've been steeped in kind of academia for so long, and it's been quite a long time since we've had someone that is speaking from the sort of academic perspective. We see a lot of health tech out there, and I just really loved that you have this like more classical background. Obviously statistics is a big part of AI and a big part of machine learning. So it's really nice to have someone with your background that isn't just kind of coming at it from private sector, but really from the academic circles, and then finding use cases and applications of this. I mean, sky's the limit, I guess, right? You're still pretty early in your career, so who knows where it'll take you. So maybe that's a good place to start. Would you mind just kind of, telling us a little bit about your background for those that don't know, and sort of what got you into being excited about statistics, or by extension, machine learning?
Sure. Yeah. So I did my undergraduate in statistics, as well as cello performance. So I was a musician before that. And then I just recently completed my Ph.D. in biostatistics. So the way I got into statistics is actually kind of interesting. I was always interested in science and math, but from a very young age, I was in music. This is the family trade. It's been playing cello since I was 3, that kind of a thing. And so it was just kind of what I was entrenched in. It was what I did all the time. And so it wasn't until college, I started doing some of this empirical musicology research. So kind of like music psychology, like how does the brain respond to music, and ended up doing some statistics for this. And then I was like, wait a minute, I really love this. This is really cool. And I wish I knew more about math. I wish I knew more about, science. And it just kind of went from there. I just realized, yeah, this is what I want to do. Machine learning in general, I guess that kind of came later. I was interested in it like conceptually since I started math, but I didn't really have, I guess, the opportunity to pursue some of these, some actually learning it until I was in my PhD program. So my actual dissertation work happened to take place out of the Medical AI and Automation Lab at UT Southwestern Medical Center, and that's really where I learned the majority of what I know about AI and reinforcement learning specifically.
And what was kind of like, I guess, what was one of the first projects you worked on that made you feel like, okay, this is a path forward for me career-wise, or was there one?
In terms of like statistics or machine learning?
Machine learning.
Machine learning, I don't know, this is probably a cliche to say, but like my dissertation project, like I ended up teaching myself a lot of stuff out of a textbook, because you get these intro machine learning classes and stuff, but once you actually start tackling a really big project. It's like, it's just an intro. Like the stuff you get in class is just like this intro. And so when I really started seeing, like in my simulation, this method that I'm using kind of works, and actually watching the thing train and watching it actually work, that was, I mean, it's still always a thrill to me when I see, anything that I've written with code, seeing something that I've made work, I get that moment all over again. So I guess that was kind of it. It was when I actually started seeing like the results of some of these projects that I've spent so much time on. Yeah.
And just to kind of, as a reference for people, what was your dissertation on specifically?
Right, yeah, probably should have mentioned that. So I was working on some methodology for designing adaptive radiotherapy treatment plans. So you've probably heard of radiotherapy and immunotherapy before as treatments for cancer. And so a recent development that people have discovered is that if you're applying these two treatments together, the effectiveness of the combination treatment depends on the timing of the radiotherapy pulses. So if you apply 2 pulses 10 days apart with immunotherapy, it's going to have a different efficacy rate than if you apply these same 2 pulses 1 day apart. And these different, the key here is that the optimal spacings for the radiotherapy doses might depend on the individual subject. So we'd like to have some way of optimizing in a personalized way these radiotherapy treatment plans. So that's what my dissertation research was really about. I used reinforcement learning, used both reinforcement learning and some, classical statistical methods, where from the reinforcement learning parlance, your state is all of the tumor growth you've observed so far and whatever other cofactors you have about that specific subject. And then the action you can take is, how many more days you wait before applying the next dose of radiotherapy. And so that's kind of the premise of my dissertation work. Yeah.
And I know we're skipping a little bit here with your intro, but I just wanted to get back to the math and the physics, because initially, that was your avenue into this, right? So did you pursue anything further with when was that break of okay, I'm into physics and I want to focus on physics versus, okay, let me see about immunotherapy and kind of the health stuff?
Yeah. So I've taken some, elective physics classes. I fell in love with them when I took one as an undergrad, and then I also took some as a graduate student. But what really made me fall in love with the specific application is when I realized that medical oncology uses the intersection of a bunch of different fields that I like. So I like, obviously, statistics and math, but you also get to use a lot of physics, you get to use a lot of computer science, and it's all mixed together in this application that I can see the direct usefulness of. And so just realizing that in this application is where I get to see the intersection of all of, these really interesting things that I'm into. And it doesn't make me, force me to pick just one like I would if I wanted to go into pure math. That's what made me kind of fall in love with it, I suppose.
And that's the thing. I mean, I think, when you and I were talking before we actually, scheduled this, I really like what you said about, I feel like now I can really take a use case that's actually, helping the world, so to speak.
Mm-hmm.
And it's still interesting. It's still something I want to do, but I see the direct urgency and kind of, I mean, it's all valuable, right? But still, I mean, it's cancer. You're helping people solve cancer. So I totally get that. I guess just based on your work and it doesn't have to be anything specific, but if you have a specific example, great. But I guess if you could distill what is AI helping you with versus where is the true premium or the true help? Do you feel like it's do you feel like it's showing you like patterns you might not have seen otherwise, or like in what way is it helping you specifically?
Helping me specifically? Yeah, I think that's really it, is that's what it does. You're right, it identifies patterns, and for better or for worse, because sometimes the patterns that it identifies are not useful. But as I'm sure we're all, aware with the situation, if you go through your data, you look at your worst performing cases and you realize your model found a loophole or something. But yeah, it's really about, I think, making sense of big data in a way that like my tiny human brain can't possibly comprehend. Like, I mean, and statistics can do this too, but AI really brings it to the next level in terms of efficiency with these huge data sets. So we have these swaths of data, like these, especially, I'm postdoc at Memorial Sloan Kettering Cancer Center, and we have these huge spatial transcriptomic data sets. And of course, when you have like whole genome sequencing, and if I look at these data, it just means nothing to me, just like if I look at it raw. But then suddenly when you apply these principles, these AI methods, machine learning, suddenly you see these patterns arise. You can do really cool stuff with them in a way that is just almost like, I understand how the method works, obviously, but it holds so much information in a way that like the human brain just can't, and that's really beautiful, I think.
Yeah, and just to kind of talk about the I guess the tech behind it, you mentioned reinforcement learning, so you're using deep learning, basically deep learning models for this, and then you said also some statistical modeling.
Yeah, so reinforcement learning itself, it has been around since I think before deep learning has, before like neural networks. It's seen a rise in popularity over the past however many years because of the introduction of like deep reinforcement learning, where you essentially use neural networks within the reinforcement learning paradigm. And so I did that as part of my work. The internal model, I suppose, of the environment that the agent uses is a neural network. And so yeah, I did that. I did use some neural networks. I'm not sure if I would call it deep learning per se, because the networks that I was using were pretty shallow. But definitely could be, for if you were to take it into a different context, apply it in a different way, you could definitely use it like that too.
But then did you also find like simpler models, like were you at any point using like linear regression or logistic regression models? Like, were you finding that like, were there certain models, I guess, that were more effective than others when you were kind of testing things out?
Yeah, so I did work on, within the kind of adaptive modeling framework, we tried some Bayesian linear and nonlinear modeling. And really there's this trade-off, I think, and well, not I think, we tested it. There's this trade-off between like robustness and like efficiency, generalizability. So the neural network, since it makes very few assumptions about the form of the data, it's going to be a lot more generalizable, but it takes a lot, the trade-off is, of course, it takes a lot more data to train. However, if you look at, for example, a nonlinear Bayesian mixed model, of course, it's going to take a lot less data to train, because it makes a lot more assumptions about the form of the data. Now, if those assumptions are correct, these can be very powerful models. But if they're incorrect, then you might not be sure that you're getting the right answer. So it's really a trade-off. There's no free lunch. But yeah, there's definitely a give and take between classical statistics and the neural network approach.
Yeah, and that's also part of why we do these, right? Because especially now, like if you follow all the marketing spin, like everyone's talking about AI, and it seems that the trend is more working towards deep learning being the kind of de facto AI model that's used, just because I guess how quickly it learns, how quickly it kind of goes through. But there's still like such an advantage to using like these simpler models. And in many cases, like machine learning models, like companies that are making products, like they're not using deep learning, they're using something much simpler than that.
Yeah.
So I do try to like remind people that like, okay, just because everything's about deep learning right now doesn't mean it's the only thing and it's the only valuable thing out there. It's just one of the tools.
Right. There's also, so it's kind of cool because there's also been a rise recently in what people are doing is they're using both in tandem with each other. So I've been reading, there's a lot of people doing this in the spatial transcriptomics world as well. You'll have this complicated Bayesian model, but then one part of the model you don't know what the structure of, so you replace that part with a neural network, and then you can train it all using and fit the parameters of the whole model using backpropagation. And so that I've seen in a lot of these high profile journals is what's really getting some attention, and what can be really powerful is using both classical statistics in tandem with the deep learning approach.
Wow. Oh, and then, and how like involved are you getting? Like, do you work with machine learning engineers yourself, or are you the machine learning engineer? Like, how does it work?
Technically, I think my title is research fellow.
Okay.
But yeah, I haven't gotten my hands too dirty yet with the actual, like my current position. I've only been here like a few weeks, but definitely we're looking at actually building some of these, VAEs, autoencoders, and working with these sorts of methods ourselves. Of course, whenever possible, if you can use something that someone else has built, that's always nice, always the way to go. But and there are a lot of cases, like often we might not actually be able to do that, or the methodology or this neural, this model might not exist yet, so we might have to do it ourselves.
Right.
Yeah, so I know there's been some of my peers do actually, they do this stuff, and it's more than likely that I'll probably end up doing that as well.
And then in your dissertation work, you were developing new applications for reinforcement learning for adaptive radiotherapy, and combining that with immunotherapy. So can you share a bit about that work with us? Like how you leveraged reinforcement learning specifically?
Yeah. So it's kind of like, I think I sort of touched on or gave a small introduction to it before. So the idea is, well, in all of our experiments, we're assuming the context for now of a tumor xenograft experiment, which is a necessary step in the preclinical development of a therapy for a solid tumor. So before you can do an experiment on humans, you have to do it in mice. So that's what we simulate first. And so the idea is you implant these set of experimental animals with tumors. You wait a bit for the tumors to grow, then you apply various treatments of interest and see what happens to each group. Now we develop and test a kind of a new method where instead of assigning treatments all to a whole group at once, you assume that these mice come in one by one. And so the idea is you observe the pretreatment tumor sequence. You treat the animal at the first time point is fixed. You see what happens, how they respond to the first treatment. And then using all of that information, you, together with your predictive model, and this might be a neural network, it might be a Bayesian model, you forecast what's going to happen to that animal under each potential treatment that you could apply in the future. So that might correspond to radiotherapy tomorrow, or radiotherapy in a week, or such and so forth. And then using those forecasted outcomes, you select the best option and apply that. And then you see what actually happens. And using that new information after you apply that treatment, you can update the parameters of the model and then recruit a new individual and start again once you've treated that animal to completion.
So those are kind of your punctuations for when you tweak your hyperparameters or make any changes to your model then?
Well, it's really, what I'm really describing here is kind of the reinforcement learning paradigm. So here, our environment, what makes reinforcement learning unique is that one of the things is that it can actually, the agent interacts with an evolving environment and updates its model like continuously in real time. So that's kind of what I'm describing here, right? So the actions, the environment, the state of the environment, if you will, is what has happened, everything you know about this individual so far. And then you're trying to manipulate the environment to get to a specific state. And that specific state you want is the one with the lowest tumor volume. And so the idea is the model can iteratively update with the new information per the reinforcement learning paradigm by updating its internal model and then interact with the environment as such.
And has anything like surprised you as you like kind of worked through that work?
Surprised me. A lot of things, I guess. Things that worked, things that didn't work. I was surprised that I ended up using R so much. That's a big.
That is surprising. Well, actually, I feel like they use it a lot in academia, R and Python.
Yeah, but as opposed to Python for like deep, because I started doing everything in Python, and then I found, for some of my simulations, actually, R can be very useful with doing a lot of your Bayesian modeling. It has a lot of like pre-implemented packages that are really nicely parallelized. So you have, they're efficient and stuff. And then it has some packages for neural networks as well that they're not super customizable. So like if you want to do anything like a custom training loop, of course, I'm going to go to PyTorch. But for like very simple out of the box stuff, R can be super useful. And that was not something I really expected to hear myself say, is doing neural networks in R. But if for certain cases, it can be pretty useful.
Yeah, I'm actually surprised about that too, because, well, I've never used R, so I really don't know anything about R. But it just seems like the ecosystem is so wide for Python. So I actually am very surprised by that.
Yeah. They can also, I also wasn't expecting how to notice how well integrated the two languages are. Like you can do like R environments in Python environments in R, a lot of stuff like that, which was something I didn't really anticipate to find.
Wow. Well, and now, as you kind of think about your work at Sloan, how do you, I guess, do you have a sense of how you want your work to evolve? Like, do you want to stay firmly in research, or would you want to get like more on the technical side? Like, or are you feeling like you're gravitating toward one or the other?
That's a good question. You mean like research versus industry, or like industry versus academia, or
yeah, well, I mean, you're working in a research capacity now. So do you find yourself liking the research side of it more, or the technical problem solving side of it more?
To me, that's the same thing.
Okay. Yeah, cool.
Yeah, research is all about like technical, creative problem solving. It's all about like, there's this gap, there's this thing nobody has done before, and so we need to find a way to solve it. So I guess to me, it's really all the same thing. Eventually, I don't know, I had kind of loosely planned to eventually step out into like research-based industry, but it really depends on like where the opportunities go and where, where my research takes me. I try not to forecast too much in that regard, because you never really know. It depends on what cool stuff you find, who you meet, a lot of other variety of factors. So,
good. Yeah. It sounds like you're open. That's good. And then I guess let's talk a little broadly about AI, from your perspective. I don't know, do you feel like you're an AI optimist or a skepticist? Do you feel excited by its possibilities more than its limitations? Like,
Yeah, well, kind of both, I guess, in different ways. So AI poses a lot of opportunities, obviously. There are a lot of cool applications of it, a lot of, cool things you can do, but there are also some very real concerns about how it's going to affect people, like from a privacy standpoint, with data sharing, a lot of these other issues, job security, things like that. They kind of point to a lot of the problem with the thing about AI is it learns so much from the data, right? Like it doesn't really invent anything new, but it really amplifies and points out these patterns. And so the problem is it kind of amplifies a lot of existing problems, like a lot of existing like social issues and problems with, I think it's really gonna it hasn't done great things for like the class divide and things like that. The barrier to entry into the world of AI is getting increasingly high. And then, there are a plethora of, other kind of issues. I'm not concerned about the robot apocalypse.
right.
I will say that. I'm more concerned about, these issues of privacy, of like selling data, and the biases that the machines are learning.
Yeah, and it's an ongoing, topic of conversation. I mean, we met at that Tribe AI event where, we were talking about kind of, what is the future of privacy, and it was it's an uncomfortable conversation, because when kind of, all the ways that automation is basically encoding, our existing biases, it's disheartening, right? Because you want to be excited and say, yeah, like we can use this to help us fight cancer, but at the same time, it's having these adverse effects as well, and it's yeah.
And one of the quintessential examples that people point to actually does happen. So I work on melanoma, which is a type of skin cancer, and one of the quintessential examples of a problem with AI is one from skin disease in medicine, where the AI was much worse at identifying skin diseases on darker skin than lighter skin. So this is just one example of the many issues you might find deploying the stuff in real life.
And is the root cause, do you think, still the same, just that there aren't enough examples of that, of melanoma on Black skin in the training data? Is it still the same?
Oh, so this isn't the example I'm quoting isn't, I'm not sure if it's from melanoma. It's not one from the data that I'm it's not from a data set that I'm personally familiar with, but there's I'm not sure. I don't think it was melanoma. I think it was a different skin disease. But it's still in the same general region of dermatology, I suppose. But this, my point is this is the sort of thing that especially in my field, AI, we always have to be on the lookout for. Always do your subgroup analysis, see who your product is working for, see which samples it's not doing well on, and figuring out why. Is a really important step in the development of any AI for medicine tool, I suppose.
And that's my hope, as time goes on. I do hope that, the developers of AI systems, or, product managers, or, whatever you want to call it, executives, I guess, that oversee, how solutions are made, they take that step to be like, hang on, is this representative? Is this fair? But that's the thing that makes me question if it will happen, right? Because it's essentially based on the honor system, based on your own values of, is that something you care about, right? But if it's not something someone cares about, then who's gonna tell them not to, right?
We have to do the social pressure.
Yeah.
No, I have hope. I think if we the key is to keep actually talking about the issues and keep like working on them and writing about them. Specifically, like, we do these workshops at conferences. We have these, at discussions on your panels, and actually figuring out ways to solve these problems. I think it's the only way to go forward, like, because AI is already here. There's no going back. So if you're amplifying all these, all you can do is work on them, and charge ahead and try to make a new path to a better future, I suppose.
And no amount of signing open letters about halting its development will actually stop any of it from continuing. I don't know if you saw that. Or you know what I'm talking about.
Yeah, I know. I'm familiar.
Okay, my last, official question before we open it up to the group, because now, I mean, you've been in this field for a number of years. So do you have, obviously we are women in AI, so do you have any advice for women that are trying to get started in their careers, that might want to follow in your footsteps?
Advice, that's very general. I would say that the more math you learn early on, the more like computer science you have. Math and computer science early on is very helpful. So I took a bunch of like pure math classes electively, and those I think just like learning how to think and problem solve that way was extremely useful. I found myself wishing that I had taken more computer science classes, though I suppose, maybe this is the trade-off. I took math instead of computer science, but that sort of stuff, very useful. Probably also like finding a good, support group, and like if you can finding like a really good mentor or PI can be really, really helpful. If you're an undergrad, you can go talk to a professor, ask about research projects, and getting your foot in the door that early can be extremely useful, and something I wish I had done sooner. So probably that. And then, I don't know. Yeah.
That's a good list. What's a PI?
Principal investigator, primary investigator. Sorry, academia talk, I suppose.
Okay, I was like, that must be an academia term.
Yeah. So it's like your research advisor, essentially, your advisor for your dissertation, or yeah.
Awesome. Cool. Well, thank you so much for sharing your work and sharing a bit about your journey with us. I'm going to pause the recording here, and then we're going to get kicked off. So I'm going to come back on. So you guys can all click back on the link, and I'll see you in a few.